Right, hello year 13. I wanted to run through this chromatography question from this paper. So first one, we need to write an equation for the reaction of concentrated nitric acid with concentrated sulfuric acid to form the species that reacts with nitrobenzene. And what we want to do is form dinitrobenzene. So what we want is this HNO3 plus H2SO4, and we crucially want to make the NO2 plus electrophile. We also form HSO4 minus, and we also form water. There is a version of this which is slightly different, but this one is absolutely fine. Okay, name and outline the mechanism for the reaction of this species. So it's talking about the NO2 plus here, okay, with nitrobenzene to form 1,3-dinitrobenzene. So a couple of key things here that we need to be really careful with in the mechanism. I'll come back to the name at the end. So we start off with the nitrobenzene, okay, circle at the center, and then we attach the original. There's already a nitro group on there, so we attach that somewhere. All right, so let's just put it there for now. Now we want to make 1,3, so that's carbon number 1, 2. So we want to join the the next nitro group there. So let's have the NO2 plus ready and waiting there. Okay, so first mechanistic arrow. Let me get a different colored pen. Is going to be from the circle, from this line here to the NO2 plus or just adjacent. Really, really key. Okay, it's not the other way. We've got an area of high electron density there in that ring, so the arrow is going to be coming from there. So something like that is absolutely fine. Okay, then the next bit's got the horseshoe structure in it, and this is where lots of people will lose a mark. So same thing again to start with. So we have the benzene there with the nitro group here, and now we've attached this other nitro group to carbon number 3. So here, remember that we've got the hydrogen still there, so draw it on, and now comes the horseshoe. So we want to have now the open circle with the plus sign inside it, but remember what it says on the mark scheme. That horseshoe can't extend beyond this carbon or that carbon there. So to make sure of that, I'm going to start my horseshoe here so it doesn't go beyond this, and I'm going to end it so that it doesn't go beyond that carbon there, and it should be facing the carbon where you've attached the nitro group, and then the plus sign there. All right, you get 1 mark for that structure. Then we want the mechanistic arrow from the carbon-hydrogen bond going into the horseshoe structure in the middle. All right, so think about what type of reaction is going on here. It's we're adding the NO2 plus, but we are removing the hydrogen, so it's a substitution, and it's electrophilic to start with. All right, so this is an electrophilic substitution. Remember that benzene doesn't undergo an addition reaction, because in an addition reaction, think about it, we've done addition with alkenes, you end up breaking the double bond, but that doesn't happen in benzene because of the stability of the ring. Right? So next, the dinitrobenzene shown were investigated by TLC. So we've got this 1,2-dinitrobenzene and 1,4-dinitrobenzene. In an experiment carried out in a fume cupboard, a concentrated solution of pure 1,4-dinitrobenzene was spotted on a TLC plate coated with a solid that contained polar bonds. So that's a key bit of information. TLC plate, it's got a solid that contains polar bonds. So your stationary phase is polar. Hexane was used as the solvent. That is key again. Think about it. Hexane. So that's C6H14. That's a hydrocarbon, so that's going to be non-polar. So we've got a non-polar mobile phase and a polar stationary phase. You get that from this part of the question. Okay, the start line drawn in pencil, the final position of the spot, and the final solvent front are shown on the chromatogram in the diagram below. All right, use the chromatogram to deduce the RF value. So measuring the distance travelled by the spot, we do it from the middle of the spot. We come out with these two numbers, 4 and 6. Okay, then it's spot over solvent, so 4.0 over 6.4. Now, if we divide that out, we get to 0.625. I can't quite explain why that is not coming out any better. Personally, I think I think they should design the question a little bit better than that. But nonetheless, this is the closest, so it's going to be that. Okay. Right, so this type of question comes up quite a lot, and it needs quite a specific answer. State in general terms what determines the distance travelled by a spot in thin layer chromatography. So it's in general terms. So in general terms, what determines how far this spot travels, or what any other spot would travel. So we are right to begin talking about the affinities for mobile phase and stationary phase, but it's to do with the balance of the two, or the relative affinity for the stationary phase and mobile phase. So we use one of those two terms, okay? What we can say is this: it's the relative, so it's, we're being comparative, the relative affinity of the substance to the mobile phase and stationary phase. So it's important that we reference both of them, not just one. I think sometimes you can get the mark for referencing one, but I think it's always best to just be sure. To obtain the chromatogram, the TLC plate was held by the edges and placed in the solvent in the beaker in the fume cupboard. The lid was then replaced on the beaker. Give one other practical requirement in placing the plate in the beaker. So it's held by the edges, and probably gloves would have been used to prevent contamination. Placing the solvent in the beaker in a fume cupboard in case the solvent is toxic. Lid was placed back on the beaker. That's to ensure that the solvent vapors are saturating the beaker. What's the one other practical requirement that we need when placing the plate in the beaker? Well, that is to make sure that the depth of the solvent is not above the baseline. Okay, so what we would say here is that the depth of solvent must be below the baseline. Okay, so two final questions on this part are more application, I would say. Okay. So a second TLC experiment was carried out using 1,2-dinitrobenzene and 1,4-dinitrobenzene. An identical plate to that in part C was used under the same conditions with the same solvent. Remember, it was a polar stationary phase and hexane was the solvent, so it's a non-polar mobile phase. In this experiment, the RF value of 1,4-dinitrobenzene was found to be greater than that of 1,2-dinitrobenzene. Deduce the relative polarities of the two and explain why 1,4-dinitrobenzene has a greater value, right? So 1,4-dinitrobenzene has a greater RF value. So what that means is that 1,4-dinitrobenzene travelled further up the TLC plate. Keep in mind that hexane is the solvent, right? So the further up you travel the plate, the stronger your affinity for the solvent. In this case, the solvent was non-polar. Therefore, the 1,4-dinitrobenzene is more non-polar. Okay? You can answer it like that, or you could answer it as an alternative. You could say that 1,2-dinitrobenzene is more polar. Either or. Okay? So we could say this then: 1,4-dinitrobenzene is less polar. Okay? The explanation. Well, it's to do with this idea. It's the idea that hexane is the solvent. The 1,4 has got the greater RF value. So put the things together, we could say that the 1,4-dinitrobenzene has a greater affinity for the mobile phase, which is hexane, which is non-polar. Okay. Right, next, a third TLC experiment was carried out using 1,2-dinitrobenzene an identical plate to that in part C was used under the same conditions, but the solvent used contained a mixture of hexane and ethyl ethanoate. Okay, so we've introduced a new dimension here, so something new into the solvent. So ethyl ethanoate, it's an ester, so we've got a C double bond O, O, then we've got CH2, CH3, then on the other side we've just got a CH3. Key thing here is that we've now got a polar bond in there, so we're now introducing something more polar to our solvent, right? So a student stated that the RF value of 1,2-dinitrobenzene in this third experiment will be greater than that of 1,2-dinitrobenzene in the experiment in part F. Now in part F it was just hexane. Now in part G we've got hexane and we've got this ethyl ethanoate, which is more polar, right? And the student is saying that the RF value of 1,2-dinitrobenzene would be greater. Are they correct? Yes, they are. Reason being, we've now made the solvent more polar. So we could say that the solvent, or stationary phase, is now more polar because we've added this ethyl ethanoate, which has got a polar bond in it, right? So the solvent stationary phase is now more polar, therefore the 1,2-dinitrobenzene now has a greater affinity to the, and again we can use solvent or stationary phase. Okay, so there we go, that's that chromatography question walked through.